Hey everyone, Mr. Hauk here. In today's video, we're going to look at an introduction to complex numbers. By the end of this video, we should be able to find and use conjugates to find moduli and quotients of complex numbers and represent complex numbers on the complex plane. Let's go ahead and get started here. So we know that in the real number system, there is no possible number that we can square to get a negative number. We know that a positive number times a positive is positive, and we also know that a negative number times a negative number is also positive. So there is no real number that can accomplish this goal, so we need a new number system in mathematics so that we can square a number and get a negative result. We call this number system the imaginary numbers. For the imaginary numbers, we have I is equal to the square root of -1. Notice that if I square both sides here, we get that I squared is equal to -1. When we combine real numbers and imaginary numbers, we get a complex number. A complex number, we'll call it Z, has the form A plus BI, where A is the real part of the complex number and B is the imaginary part of the complex number. Now, it is entirely possible for either part of the complex number to be 0. When the real part is 0, the number is purely imaginary. So imagine that, A was 0. Well, we would just have BI, so we only would have an imaginary part of the complex number. When the complex part is 0, so when B is 0, the number is simply a real number. Now, every complex number has another complex number associated with it, known as the complex conjugate. You find the complex conjugate of a complex number by changing the sign of the imaginary part. Let's look at a couple examples here. So here in our first example, we want to find the complex conjugate of 3 minus 5i. Well, the imaginary part is minus 5i. So let's go ahead and change the sign from a negative to a positive, which would give us 3 plus 5i. Notice we did not mess with the real part or the a term. In the second example, we want to find the complex conjugate of -8 plus 1/3 i. Well, again, let's go ahead and change the sign of the imaginary part. So we will have -8 minus 1/3 i. Once again, notice we are not changing the sign of the real term, only the imaginary term. In our third example, let's find the complex conjugate of 17i. Well, notice that 17i is the same as 0 plus 17i. So to find the complex conjugate, we would have 0 minus 17i, or simply just -17i. And in our fourth example here, let's find the complex conjugate of 37. Well, notice that 37 would be the same as 37 plus 0i. Well, we don't have an imaginary part, so there's no imaginary term to change the sign of. This would just stay 37. So we want to answer the question, why are these complex conjugates important? Well, let's see through a multiplication example. Here we want to multiply 4 minus 7i times 4 plus 7i. And I'm going to use an area model to do this, so I'm going to go ahead and set up a little area, a box. I don't like that. Let's try one more time here. Yeah, I like that. Okay, so in my area model, I'm going to be multiplying 4 minus 7i times 4 plus 7i. Going through and doing our multiplication, 4 times 4 is 16. 4 minus 7i is -28i. 4 plus 7i is 28i. And 7i times -7i is -49i to the second power, or I squared. So going through here, let's go and do some calculation. So we can see that the -28i and the +28i will cancel each other out. So I'm going to go ahead and cancel those out here. And we are left with 16 minus 49i to the second power. Well, by definition of I, since I is the square root of -1, and we saw that I squared is -1, we can substitute I squared with -1. This would give us 16 minus 49 times -1, which is 16 plus 49, which would give us 65. So let's see what really happened here, because remember, we want to answer the question, why might these complex conjugates be important? Because notice we multiplied 4 minus 7i times its complex conjugate 4 plus 7i. Now what happened? We multiplied two complex numbers that had imaginary parts and noticed that the product was a purely real number. So it turns out that multiplying I'm going to write this down here, multiplying a complex number times, let's say by, let's be grammatically correct, multiplying a complex number by its complex conjugate will always result in a purely real number. Right? And again, we saw that here. We had a complex number times its complex conjugate, and the result was a purely real number, 65 in this case. So we use complex conjugates when performing division with complex numbers. Since we want to represent complex numbers in the form a plus bi, we call that standard form, we do not want to have any imaginary numbers in the denominator of any fractions, since the imaginary part of a complex number will go last in standard form. Let's look at a couple examples here. So we want to write, let me get my normal colors here. We want to write the quotient 3 plus 5i divided by 4 minus 7i in the form a plus bi. So let's go ahead and start it off here. 3 plus 5i divided by 4 minus 7i. And what we're going to do is we're going to multiply the top and bottom, the numerator and the denominator, by the complex conjugate of the denominator. So the complex conjugate of 4 minus 7i is 4 plus 7i. So let's multiply top and bottom by 4 plus 7i. Now, let's go through and multiply. So we're going to multiply the numerator times the numerator. I'm going to go in and just use FOIL. So first times first, that's going to be 12. Outside times outside, 3 times 7i, that's going to be 21i. The insides, 5i times 4, that's 20i. And then the last terms, 5i times 7i, that's 35i to the second power. In the numerator, we actually did this example right here on the first page of our notes. We did 4 minus 7i times 4 plus 7i, and we ended up getting 65. So just to cut down on a little bit of our work, we know this will be 65. All right, starting to reduce. Well, we know 35 times I to the second power. We know I to the second power is -1. -1 times 35 is just a -35. So we're going to have 12 minus 35 plus 41i. I'm going to go ahead and combine these terms with I together over 65. 12 minus 35, that's going to be -23 plus 41i over 65. And again, we want to write it in the form a plus bi. So what I'm going to do is I'm going to go ahead and separate the fraction using this denominator 65. So this will be -23 over 65 plus 41i over 65. And notice that this is now in the form a plus bi. Here's our real part, -23 over 65. Here's our imaginary part, 41 over 65. All right, let's try a second example just to get a little more practice under our belt here. So we want to write the quotient 7 plus 3i divided by 9 minus 5i, again in standard form, a plus bi. So 7 plus 3i divided by 9 minus 5i. Again, we want to multiply numerator and denominator by the complex conjugate of the term that's in the denominator, so 9 minus 5i. Complex conjugate of 9 minus 5i is 9 plus 5i. And let's go through and start doing our multiplication. Again, I'm going to use the FOIL method. 7 times 9 would be 63. 7 times 5i is 35i. 3i times 9 is 27i. And then 3i times 5i is 15i to the second power. In the denominator, 9 times 9 gives us 81. 9 times 5i gives us 45i. Negative 5i times 9 gives me negative 45i. And then negative 5i times 5i would give me negative 25i to the second power. All right, doing some reducing here. Again, we know that 15i to the second power, since I to the second power is negative 1, that's a negative 15. 63 and negative 15 is going to give us 48. So we get 48 plus 35i plus 27i, that's going to give us 62i. And look into the denominator. Well, let's go ahead and notice some of these terms are going to cancel. 45i and negative 45i, they cancel. Again, we want to see that because we want to see the imaginary numbers canceling in the denominator. That's the whole point of using our complex conjugate. Okay. Same deal here. Negative 25i squared. Well, we know I squared is negative 1. Negative 1 times negative 25 is positive 25. So we have 81 plus 25, which is 106. And now let's go ahead and separate the fraction. We again want 48 over 106 plus 62 over 106i. All right, we can reduce these fractions. 48 over 106 is going to be 24 over 53. 62 over 106 is going to be 31 over 53. So we can see real part 24 over 53, imaginary part 31 over 53. All right, so that's the importance of complex conjugates. They help in division of complex numbers. Now let's talk about the complex plane and the modulus. So for the complex plane, the horizontal axis will be the real axis, so the axis of real numbers, and the vertical axis will be the imaginary axis. So on the imaginary axis, imagine this was going, 1i, 2i, 3i, 4i, and so on and so forth. Okay, same thing in the negative direction, negative 1i, negative 2i, and so on. Okay, so we want to go ahead and get some practice graphing complex numbers. Let's go ahead and graph and label the following complex numbers on the complex plane. So point A is going to be 5 plus 9i. And notice all we have to do is intersect the real part with the imaginary part. So we're going to go to 5 on the real axis. 1, 2, 3, 4, 5. And then we're going to go up 9 on the imaginary axis. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there. There's point A. Same thing with point B. We want to go negative 3 on the real axis, negative 7 on the imaginary axis. Let's get a different color here. So negative 3, negative 1, negative 2, negative 3, then negative 7 on the imaginary. 1, 2, 3, 4, 5, 6, 7. Right there. So that's point B. Point C, 6 on the real axis, negative 8 on the imaginary axis. Well, we already know that this was 5, so this will be 6 right here. And then negative 8 will take us down right there. And let's get a different color. Let's do red, sure. All right, there's point C. And point D, let's do that in pink. Why not? Negative 9, and then we will go to positive 2. Negative 9 on the real axis, positive 2 on the imaginary axis. Point D right there. And let's just double count that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, we're good to go there. Okay. So those are points in the complex plane. Let's talk about something called the modulus. So given a complex number z, z being a plus bi, the modulus is denoted by z in what looks like absolute value brackets and is defined by the modulus z, also represented by the lowercase letter r, is the square root of the real part a squared plus b squared, the imaginary part. Geometrically speaking, the modulus is the distance of the point from the origin in the complex plane. So if I wanted to find the modulus of point A, I'd look at the origin, I'd look at point A, it would be the distance from the origin to point A. Now notice we can find the modulus with Pythagorean's theorem because we have a right triangle. That's exactly where this is coming from. That's Pythagorean's theorem. We'll notice that A being the real part, B being the imaginary part, R being right there, that's how we're getting the modulus. So let's find the modulus of each of those points up top, starting with point A. So we're going to say A is equal to, and we saw that A was 5 plus 9i, so this is the square root of 5 squared plus 9 squared, the A term and the B term. Well, it's going to be 25 plus 81, which is 106. We know 106, that's just 53 times 2. There's going to be no combination of perfect squares, so square root of 106 is going to be already simplified. Let's see, B, we made blue. And let's go ahead and say, and really I should be a little more careful over here with what I did with A. Let me go ahead and say this is A. And we're saying R equals. Okay, just want to be a little careful with my notation. So for point B, R equals, let's see, point B was negative 3 minus 7i, so we're going to take the modulus is negative 3 squared plus negative 7 squared. Let's see, that's going to be 9 plus 49, which is square root of 58. 58. Square root of 58 should already be simplified if I'm remembering correctly. Yep, because that's going to be 29 times 2. 29 is a prime number, so can't be simplified any further than that. Point C is 6 minus 8i. We did point C in red. So we're going to have R, the modulus, is equal to square root 6 squared plus negative 8 squared. That's going to be 36 plus 64, that's 100, and we know the square root of 100 is 10. So once again, just to kind of bring it back to this, this is saying that if I looked at the origin, if I looked at that point on the complex plane, the distance from the origin to that point would be 10. Notice these are all positive numbers. This is a distance. And then lastly, let's look at point D. Point D was negative 9 plus 2i. So the modulus R is going to be the square root, negative 9 squared plus 2 squared. 9 squared, negative 9 squared is going to be 81. 2 squared is 4. That's going to give us square root of 85. That should not simplify any further because 85 is 17 times 5. 17 is prime. Yeah, so we should be good there. So again, each one of these represents a distance from the origin on the complex plane to that point. All right, so let's talk about something called polar form. So far, we have been working with complex numbers in the form, z, the complex number, equals a plus bi, and we call this rectangular form. Okay, we call this rectangular form. Now, in the image to the right, again, r is the length from the origin to the point AB, which is the point a plus bi in the complex plane, and theta is the angle made with the real axis. Again, we call r the modulus, and we're going to call this angle, theta, the argument. So, using our trigonometric ratios, let's represent a and b in terms of r, the modulus, and theta, the argument. So, if I'm looking here, we know that cosine of the angle, well, we know cosine is the ratio of the adjacent leg, which would be a, divided by the hypotenuse, which would be r, 90-degree angle here. So cosine of theta equals a over r. If we multiplied both sides by r, notice that we would get a equals r times the cosine of theta. That's going to be important. I'm going to go ahead and box that. And I want the fancy box with the shading. There we go. Next, same deal here. We can say, okay, well, the sine of theta, we know sine is the ratio of the opposite leg, which is b, divided by the hypotenuse, which is r. So sine of theta equals b over r. Again, multiplying both sides times r on both sides. This gives us that b is equal to r times the sine of theta. Okay. Again, I'm going to box it, and I want the fancy shaded box, because we're going to be using that here momentarily. Let's also go ahead and derive a quick little formula for theta. We know that if I took the tangent of theta, I know the tangent of theta would be b divided by a, the opposite leg divided by the adjacent leg, and I know that theta would then be the inverse tangent of b divided by a. So let's write that down as well. Theta is equal to the inverse tangent of b over a. Beautiful. So let's do some substitution here. Again, we know that in rectangular form, a complex number is a plus bi. Let's go ahead and replace a with r cosine of theta, and let's replace b with r sine of theta. Notice that both of these terms have an r in common, so I can factor the r out, and I get r times cosine of theta plus I sine of theta. We call this z equals r times cosine of theta plus I sine of theta. We call this the polar form of a complex number. Let's get a little bit of practice here. So here we have a complex number in rectangular form, 3 square root of 3 plus 3i. Let's go ahead and write it in polar form. Let's get blue here. So first, let's go ahead and start by finding the modulus. The modulus r is equal to the square root. A squared plus b squared, we know a is 3 square root of 3. So 3 square root of 3 squared plus 3 squared. This is going to give us, well, let's think about this here for just a second. 3 square root of 3 squared, that's 3 square root of 3 times 3 square root of 3. 3 times 3 gives us 9. Square root of 3 times square root of 3 gives us 3, so that's just 9 times 3. We know 3 squared is 9. And 9 times 3, that's 27. 27 plus 9, that's going to be 36. So we get square root of 36, which we know is simply just 6. So I'm going to circle that. That's important. That's the modulus. Again, we need r for polar form. We also need theta. So we know that theta is simply the inverse tangent of the b term divided by the a term. Again, b is right here. It's 3. A is right here. It's 3 square root of 3. So we're going to do the inverse tangent of 3 over 3 square root of 3. Well, this is just the inverse tangent. Let's see. 3 and 3 reduce with each other. It becomes 1 and 1. So this is just the inverse tangent of 1 over square root of 3. We know that we don't like square roots in the denominator. Let's multiply top and bottom by square root of 3. And this is going to give us the inverse tangent of root 3 over 3. Now, let's go ahead and take out our unit circle. Give me just a moment to grab that. So let's see, blah, blah, blah. 1A, unit circle reference guide. Awesome. So going back to our notes, we want to find the inverse tangent of square root of 3 over 3, or in other words, which angle on our unit circle has a tangent of square root of 3 over 3. Well, square root of 3 over 3, for the tangent values, I can see one is here at 30 degrees, and I can see another is here at 210 degrees. So which one do we pick? Well, let's think about it here for a second. We have the point 3 root 3 plus 3i. Real part 3 square root of 3, imaginary part positive 3. Well, this is positive, this is positive. If I were to graph it in the complex plane, it would be in quadrant 1. So I want 30 degrees because that's in quadrant 1. So theta is 30 degrees. I'm going to circle that. And now let's put it all together. We know that z, the complex number, is r cosine of theta plus I sine of theta, which is going to be 6 cosine of 30 degrees plus I sine of 30 degrees. Beautiful. And I even got the shaded box. Awesome. All right, let's try another example. Write in polar form, 5 root 3 over 2 minus 5 halves I. Same thing, let's go ahead and look for the modulus first. So r, the modulus, is equal to the square root. We're going to have 5 root 3 over 2 squared plus negative 5 halves squared. All right, let's do some mental math here. 5 root 3, not mental math, I'm not going to do that in my head. 5 root 3 over 2 times 5 root 3 over 2. 5 and the 5 gives us 25. Root 3 times root 3 gives us 3. So 5 times 3, that's 75. 75 over 4. Plus, same deal here, negative 5 halves times negative 5 halves. That's going to be 25 over 4. Well, 75 over 4 plus 25 over 4 is 100 over 4, which is the square root of 25. And we know the square root of 25 is simply just 5. So the modulus is 5. Now let's calculate theta. So theta is the inverse tangent of the b term divided by the a term. Negative 5 halves divided by 5 root 3 over 2. Wow, that looks kind of messy. Let's go ahead and simplify that. This is the inverse tangent of negative 5 halves times 2 over 5 root 3, doing our whole keep, change, flip business. Notice that 2's will cancel, 5's will reduce to 1's, so this is really the inverse tangent of negative 1 over root 3, which, multiplying both the top and the bottom by square root of 3 over square root of 3, because we don't like the square root there, this is going to be the inverse tangent of negative square root of 3 over 3. So once again, hopping over to our unit circle, negative square root of 3 over 3 happens here at 150, as well as here at 330. But notice, this is a positive and a negative. That's the same as quadrant 4, so we definitely want the 330 degrees. So theta is 330 degrees. I'm going to circle that because that's important. Throwing it all in, z equals r cosine theta plus I sine of theta. This gives us 5 cosine of 330 degrees plus I sine 330 degrees. Beautiful. All right. So those two examples were both going from rectangular to polar form. Let's look at one example real quick going from polar form to rectangular form. Notice this is going to be pretty easy because all we really have to do is take the modulus and distribute it here. So first, let's go and find the cosine of 150 degrees. Here's 150. Cosine is the x value, negative square root of 3 over 2. So simplifying, this is 2 times negative square root of 3 over 2. Plus I times, well, the sine of 150, again, 150, sine is the y value, that's going to be 1/2. So sine of 150 degrees is 1/2, and let's go and distribute the 2. So 2 times negative square root of 3 over 2, the 2's will cancel with each other, we'll just get negative square root of 3. Same deal here, 2 times 1/2 I, the 2's will cancel, we just get 1 times I, which is I. Excellent. So let's look at polar coordinates now. Note that here in polar form, our graph is no longer a grid of rectangular coordinates. Now the plane is a series of concentric circles around a central point called the pole. Here's the pole. Each circle represents one radius unit, and the lines represent the angles from the unit circle. To graph a point on the polar plane, we locate the angle we are interested in, determine where the radius intersects the angle, and then we plot the point. So here's a couple examples. Let's go ahead and plot point A, which is 2 cosine of 60 degrees plus I sine of 60 degrees. I'm going to do this one in blue. So again, let's find 2. So here's 1, here's 2. And we want to put a point at the intersection of 2 and 60 degrees. So there would be point A. Very, very simple. Point B, I'll go ahead and do in green here. So the modulus here is 4. 1, 2, 3, 4. Okay. And we want to go to 240 degrees. So, oh, that was terrible. 240 degrees, that's right here. Let's put a point right there. That's point B. And then lastly, and we'll do this one in, I'll go with purple here. We want to put point C at 2 root 3 minus 2I. Now notice this is in rectangular form. We need to go ahead and change it to polar form first. So let's go through that exercise. For polar form, we need the modulus R and the angle theta. Let's start by finding the modulus R. So R would be the square root 2 root 3 squared plus negative 2 squared. Well, 2 root 3 times 2 root 3, that's going to be 4 times 3. Negative 2 squared, that's a positive 4. This is the square root of 16, which we know is positive 4. So we know the modulus is positive 4. Let's find the angle theta. We know it's going to be the inverse tangent of the b term over the a term. That's going to be the inverse tangent of negative 2 over 2 root 3. Well, we can see here that the 2's will cancel, leaving a negative 1 in the numerator. So we have the inverse tangent, negative 1 over root 3. We don't like square roots in the denominator, so let's multiply top and bottom by square root of 3. This gives us negative root 3 over 3. And I'm just going to go ahead and check real quick. This is a positive and then a negative for the real part, then the imaginary part. That'd be the fourth quadrant. So we want to find in the fourth quadrant which angle has a tangent of negative root 3 over 3. That would be 330 degrees. So angle theta is 330 degrees. Putting it all together in polar form, we would have 4 cosine of 330 degrees plus I sine of 330 degrees. And now let's go plot that point on our polar grid. That's point C. We can see that the modulus is 4. 1, 2, 3, 4. So we know we're going to be on this ring right here. We're going to go to 330 degrees, which is right there. And that will be point C. There we go.